In this video, I will discuss the factors affecting the variations of atomic radii across a period and also going down a group of elements. I will also discuss the size of an atom compared with its cation or its respective anion. Hey, I'm Teacher Tan. If you like my videos, do remember to click on the subscribe button below so that you won't miss any notifications as I update my channel. From these periodic tables of elements, there are a few deductions that we can make. First is, as across the period, the atomic radii decrease. Second, as going down a group, the atomic radii increase. And as going across a first row of transitions elements, the atomic radii remains almost the same. Why? In fact, there are two factors affecting the variations in atomic radii. For across a period, the effective nuclear charge will be the dominating factors. When going down a group, the shielding effect is the dominating factor in affecting the atomic radii of elements. Before we look into details how these two factors are affecting the atomic radii of elements, there are a few terms that we need to understand first. The first term is nuclear charge with the symbol Z. Nuclear charge refers to the full attractive forces experienced by the outermost shell's electrons due to the positive charge of the nucleus. In the nucleus of an atom, there are protons, and the protons are positively charged, and these protons will attract the outermost shell's electrons, which is negatively charged, and the full attractive forces caused by this positively charged nucleus on the outermost shell's electrons is what we call as nuclear charge. The second term you need to understand is shielding effect or screening effect with the symbol S. Shielding effect or screening effect refer to repulsive forces experienced by the outermost shell's electron from the inner shell's electrons. Outermost shell's electrons is negatively charged. Besides experience the attractive forces by the nucleus, it is also experience the repulsive forces by the inner shell's electrons. And the repulsive forces by the inner shell's electrons on the outermost shell's electrons is what we call as shielding effect or screening effect. The last term you need to know is effective nuclear charge, ZAF. What is effective nuclear charge? It is the net attractive force experienced by the outermost shell's electrons after taking into account the repulsions by the inner shell's electrons. To determine ZAF, we can use the formula ZAF equals to nuclear charge minus the shielding effect. For example, for this element, there are 15 protons in the nucleus, and that 15 protons represent the nuclear charge of the element. And for this atom, there are 10 inner shell's electrons. And that 10 electrons represent the shielding effect on the outermost shell's electron. 15 minus 10 will give us positive 5. So basically, this positive 5 refers to the net attractive force that is experienced by the outermost shell's electrons. Now we move on to determine the effective nuclear charge of period 3 element. To determine effective nuclear charge, we are still using the formula effective nuclear charge equals to nuclear charge minus the shielding effect. The nuclear charge we can get from proton number, and the shielding effect we can get from the number of inner shell's electrons. For example, sodium with the proton number 11, so the nuclear charge is equals to 11. And the outermost shell's electron for sodium is in 3s1. Hence, for sodium atom, there are 10 inner shell's electrons. There are 10 inner shell's electrons in 1s2, 2s2, 2p6. Therefore, the shielding effect for sodium is 10. To calculate ZAF, the nuclear charge 11 minus the shielding effect 10 to give us positive 1. So the ZAF for sodium atom is therefore positive 1. To determine the effective nuclear charge for magnesium, again we use the formula nuclear charge minus the shielding effect. For the nuclear charge, we can determine from the proton number. The proton number for magnesium is 12, therefore the nuclear charge for magnesium is 12. And the outermost shell's electrons for magnesium is in 3s2. Hence, for magnesium, it also have 10 inner shell's electron in 1s2, 2s2, 2p6. And therefore, the shielding effect for magnesium is also 10. To calculate the Z for magnesium, we just use the nuclear charge 12 minus the shielding effect 10 to give us positive 2. So the effective nuclear charge for magnesium is positive 2. For aluminium, we do the same thing. The nuclear charge equals to the proton number. So the nuclear charge for aluminium is 13. And the outermost shell's electrons for aluminium is in 3s2, 3p1. Therefore, for aluminium, it also have 10 inner shell's electron, and the shielding effect for aluminium therefore is 10. To determine the effective nuclear charge, the nuclear charge 13 minus 10 to give us positive 3. And therefore, the effective nuclear charge for aluminium is positive 3. For silicon, again, the proton number determines the nuclear charge. So the proton number of silicon is 14, so the nuclear charge for silicon is 14. And the outermost shell's electrons for silicon is in 3s2, 3p2. Therefore, silicon also have 10 inner shell's electron, and the shielding effect for silicon is also 10. To determine the effective nuclear charge, the nuclear charge 14 minus the shielding effect 10 to give us positive 4 as the effective nuclear charge for silicon. We repeat the same thing for phosphorus, sulfur, chlorine, and argon. So this is the effective nuclear charge of elements across period 3. And we can see that as across the period 3, the number of protons increases. And as the number of protons increases, the ZeV increase. So as the ZeV increase across the period, the attractions of the nucleus on the outermost shell's electrons become stronger. The distance between the nucleus and the outermost shell's electrons become closer, and therefore, as across a period, the atomic radii decrease. So, effective nuclear charge is the dominating factor in affecting the variations in atomic radii of elements across a period. As across a period, the number of protons of elements increases, and this will cause the effective nuclear charge of elements to increase. As the effective nuclear charge of elements increase, means that now the attractions of the nucleus on the outermost shell's electrons become stronger. As the attraction becomes stronger, the distance between the nucleus and the outermost shell's electrons will become closer, and this then will cause the atomic radii to decrease as across the period. When going down the group, shielding effect will become the dominating factors. When going down the group, the number of shells filled with electrons increases. This can be seen by increase in the principal quantum number of the elements. As the number of shells filled with electrons increases, the shielding effect of elements increase. This will cause the attractions between nucleus and the outermost shell's electrons becomes weaker, and the distance between the nucleus and the outermost shell's electrons becomes further, and the atomic radii therefore increase as going down a group. Now we move on to look at atomic radius versus ionic radius of an element. For example, potassium and potassium ion. It can be seen that potassium ion has relatively smaller size than the potassium atom. Why? It is because to form potassium ion, one electron is being removed from the potassium atom. When one electron is being removed from the potassium atom, means that now in potassium ion, there will be less electron-electron repulsions. As the electron-electron repulsions in potassium ion is less, it means that now the attractions of the nucleus on the electrons in potassium ion is stronger than in potassium atom. As the attractions of the nucleus on the remaining electrons in potassium ion is stronger, it will cause potassium ion to have smaller size than the potassium atom. How about atoms and its anion? For example, chlorine atom and chloride ion. Chloride ion has relatively larger size than chlorine atom. Why? It is because when forming the chloride ion, one electron is being added into chlorine atom. With this one electron added, chloride ion is expected to have greater electron-electron repulsions than chlorine atom. This increase in electron-electron repulsions in chloride ion causes the attractions of the nucleus on the outermost shell's electrons in chloride ion to become weaker than in the chlorine atom. As the attractions becomes weaker, it is expected for the chloride ion to have bigger size than chlorine atom.